In this film, I plan to summarize basic information about interrupts, which are one of the most important and sometimes complex things on microprocessors and assembly programming and any programming. And the examples given in the slide will include routines or emulators in 8085 or 8086 microprocessors. In summary, in this material, hardware and software interrupts and their implementations are summarized by using their usage in these microprocessors, which are classical 8-bit and 16-bit microprocessors of all times. So in order to fully understand the topics covered, there should be sufficient knowledge about the following concepts. The first one is the most important one, binary and hexadecimal number system, and microprocessors 8085, 8086, and special registers. And AX and BX are extremely important because some parameters of the interrupts are stored in those registers, and the other 16-bit registers are also important. And special other 16-bit registers like code segment, extra segment, instruction pointer, program counter are also important. As well, and subroutines should also be studied before knowing details of the interrupts. What's the meaning of interrupt? In short, interrupt is an event that causes the processor to suspend its present task and then transfer control to a new program called interrupt service routine, ISR. So that interrupt service routine actually like a subroutine, but it's not written by the code developer. It's written or factory loaded by the microprocessor production companies. In general. Short form of interrupt is INT. It has a range of 8-bit minimum and maximum values. Their hexadecimal equivalent symbols are 00 hex to FF hex. Before int is executed, AH, which is the high byte of the AX register, usually contains a function number that identifies the subroutine. So there should be special care about the contents of AH before calling that interrupt. Otherwise, there may be errors in the implementing the interrupt. Each interrupt must supply a type number, which is used by the processor as a pointer to an interrupt vector table. So interrupts are stored in vector tables with type numbers to determine the address of the interrupt service routine. So this is the subroutine part. So this is like a lookup table, and this is the row number of item number of that in the lookup table. Okay, interrupt vector table can be shown in a memory map. So each address is its type number from 0 to FF, from the lowest to highest value. So they contain in multiple registers pointers to interrupt service routines. Usually these are 4-byte numbers, and they also point to the service routine which is stored on other part of the memory. So there's a kind of twofold nesting here: vector type number, pointers, and service routines. So these routines are executed. So it's a double nested subroutine. Interrupt is a technically double nested subroutine. One cannot memorize all the interrupts. Usually they are given in tables, and in your textbook, at the end of the textbook, in Appendix D, the interrupts, original IBM PC interrupt system are given from interrupt type number 0 to FF, and their logical address are given with the segment number and offset number, and physical address can be calculated by using these numbers. So explanation or the result or purpose of this interrupt, all these interrupts are given. So for example, interrupt 0 is divide error, usually divide by 0 error. Interrupt number 1 is single step, which is very frequently used in debugging. So when we use emulator 8086, if you run the program in single step mode, after every single step, interrupt 1 is created, so program stops at that point to show some values. In our course in the university, interrupt number 10 hexadecimal, interrupt number 17 hexadecimal, 16 hexadecimal, and 21 hexadecimal are the most frequently used ones. So we will concentrate on these interrupts. Not all the interrupts are this video's concern. Some of the interrupts are not used, so the list is open for future developments. So as a result, our common interrupts in this slide are interrupt 10H for video services, which is for monitor or display, interrupt 16 hex for keyboard, 17 parallel printer services. Actually, parallel printers are almost no longer used, but those are classical printers. So in order to understand the logic behind it, we may have a look at them. And again, interrupt 21 DOS services are again not frequently used, but we'll have some applicable examples, useful examples in a DOS screen or DOS window during example show off. So the first one, interrupt 10 hex, which is related to the video services. At the first place, some numbers should be placed in high byte of AX register, then according to the function other registers are set, then the line containing this, okay, in the program segment, calling this line performs the subroutine for this interrupt for video services. Registers are not used by the function as inputs, outputs are not affected. They are burned in the ROM BIOS, so those are factory set subroutines and used to communicate with the computer's screen video. Manipulation of screen text graphics can be done via this interrupt. Among the functions associated with this are changing character, background color, clearing screen, changing the location, so let's underline all, changing location of the cursor, etc. So we can play with the characters, symbols, colors, etc. on the screen. Everything are adjusted by putting a specific value in register AH. This is the most important part. So if you fail to adjust the correct value to AH, that interrupt will be a big problem for you. So in short form, INT 10 hex, -03 means first we store 03 hex into AH, then we set other register values, etc. Then we call the interrupt. Okay, this is the typical format. Move AH 03, move BH 00. So this is also equivalent to this because decimal and hexadecimal 03 are the same. Registers DH and DL will have the current row and positions, and CX provides information about the shape of the cursor. So if we add more values to these registers, then we change the shape of the cursor. So for this interrupt, we get the position, cursor, and size. Value in the B register is related to page number, and D register contains rows and columns. C register contains cursor, start line, and bottom line. Another interrupt 1H, this time AH06 value, scroll as screen windows. Move the date on the video display up and down as the screen is rolled at the bottom is placed by a blank line. So for this register in the emulator, we do have 25 rows starting from 0 to 24 and 80 columns. The column 0 starts from the left side and 7-9 starts from the right. So the cursor upper left is here 0 0, down right is 24,79. Line scroll cannot be recovered, so if you scroll something you cannot get them back. So AL this time, before calling that int10h, AL has the number of lines to scroll. Only exception is AL00 window will be cleared. BH video attribute of blank rows. C register contains row column of the upper left corner. D contains row column of the lower right corner for the scroll. So if you summarize this part, 06 and 07, this is the opposite. So 06 scrolls up window, 07 scrolls down window, and input registers are AL, BH, C, and D, X registers. In another different parameter, the same interrupt, OA, print characters, interrupt, we write one or more characters at the current cursor position. This function can display any ASCII character. AH function code, and AL is the character to be written. So by storing suitable information to AX register, we can change the code or character from the ASCII table. MBH has the video page. C, if used, it stores the repetition factor, how many times the character will be printed. So you can have multiple characters. You don't have to write many lines to write the same character. You just change the value in the register CX, and this is the little summary of the information that's given in this concept. So interrupt 1 0 hex is over. The next one is again very frequently used interrupt of 16H, which is related to keyboard services. So we may check a key press when AH01. So first we move 01 to H, then we call this interrupt. Upon return, zero flag is 0 if there's a key press, and we can check in the program whether a key is pressed at that moment or not. With an infinite loop, if zero flag is checked and found to be 0, then the program moves to the next line or next routine to store or sense the key press. Which key is pressed? To do that, this interrupt function can be used immediately after the call to int with AH01 interrupt 6. Upon return, AL contains the ASCII character of the pressed key. So we can have an interaction, and the ASCII code of the key press can be stored in the register. So this is the summary of the information given in the 16H keyboard service interrupt. Get a stroke for register AH, high byte of A, BIOS scan code, and low byte ASCII character code are displaced, and it's zero flag 0. There's no keystroke there is keystroke available, and zero flag 1 means no keys pressed yet. And after this, register A stores the character codes. The next interrupt is interrupt 2.1 hex for the DOS functions. Actually, I skipped parallel printer interrupts because parallel printer is not used nowadays. So DOS functions are very widely separated. Many examples can be found. It opens a new DOS window with graphical or character, etc. When the operating system is loaded, this interrupt can be invoked to perform some extremely useful functions. They are commonly referred as DOSINT 2.1 hex function calls. The difference between 1.0 hex and DOS 2.1 hex are the main function call or BIOS ROM based calls. In 2.1 hex can send a set of ASCII data to the monitor, and we set AH09 hex and DX offset address in the ASCII data that displays ASCII data string pointed by DX until it encounters the $. So you can activate some string operations with indeterminate length if we have an end of string character reserved to be a $. So to output only a single character, 02 is put in AH, and DL is loaded with character to be displayed. So for more characters, we set a string, a data string in the program. The only requirement is at the end of the string we place $, and onto the screen all the characters are written. That means we can display any message to the screen. There's a program in the book, but I think the characters are so small to see. It's a simple display program, and there's a message. Message is this is a test of the display routine, and at the end there's a $. If you miss this $, the program crashes. It cannot or it prints out all the characters till it finds a $. In the memory, if there's any. So it moves data to A register, D register, etc. Then clears, call clear. Clear means we move other values to the registers, then invoke int 10H to clear all the screen. Then call cursor means cursor is placed to any point that we desire. Then we display this message at some specific location on the screen, which is row 18, column 4FH, or like this, DX. It's set here. Another option of DOS21 hex option 01 inputs a single character with echo. This function waits until a character is input from the keyboard, then echoes it to the monitor. After an interrupt, the input character will be in AL, low register of A. Or in another interrupt21 option OA or 09 hex inputs or outputs a string of data stored at DSDX, data segment offset register DX, whatever the contents of these register, this is the offset address of the data are located. And for the other one, for both of them, DX has the offset address of the data of the string. Again, this string should end with a $sign. So these are the symbols for single character echoing or string outputting in that interrupt. Well, whatever the interrupt is, the interrupt ends, like all subroutines, with I return. And in those return values, the registers are stored to their original values, and they are stored in stack pointers 6 addresses. All the flags, addresses, return addresses, segment addresses are backloaded to the system. So this is what's about interrupts, and these information are compiled from various internet or textbook resources, including some books about microprocessors, some lecture notes in the university, etc. And preliminary slide preparation were made by Tuba Demir, thanks to her, and slide finalization, this narration and film preparation were made by myself. And equipment infrastructure has been generously given by Hacettepe University Department of Electrical and Electronics Engineering. Please feel free to send comments to my email address, and future desires for the problematic issues in microprocessors and programming. So maybe, hopefully, I can prepare a new movie for your requirement or request. Thanks a lot.